For centuries, time was perceived as a fixed, absolute entity. Isaac Newton, one of history's most influential scientific minds, viewed time as a constant force ticking uniformly for all beings, everywhere. His clockwork universe depicted time as a straight, unchanging line, and this view remained unchallenged until the early 20th century when Albert Einstein's theory of relativity revolutionized our understanding of time. Einstein's work revealed that time is not absolute, but relative, intertwined with space to form a single continuum known as spacetime. According to relativity, time can stretch or compress, speeding up or slowing down depending on the observer's speed or proximity to massive objects. For example, an astronaut traveling near the speed of light would experience time at a slower rate than someone standing still on Earth. This profound realization forever changed our understanding of the universe, discrediting the idea of an absolute, universal time. However, some modern physicists, such as Carlo Rovelli, believe that even Einstein's concept of relative time does not go far enough. Rovelli argues that time may not exist at all. In his book, The Order of Time, he suggests that time is a human construct, a mental framework we use to make sense of the universe's chaotic reality. This radical view is rooted in modern physics and quantum mechanics, where the concept of time becomes increasingly elusive. The issue of time's nature becomes most apparent when comparing general relativity and quantum mechanics to pillars of modern physics that describe the universe in very different ways. General relativity treats time as a fundamental part of spacetime. It flows, changes, and is affected by gravity and motion. But in quantum mechanics, time is less concrete. Quantum systems do not rely on an intrinsic ticking clock. Instead, they evolve according to probabilities and quantum states, and measuring the passage of time requires an external observer with a clock. This creates a profound paradox known as the problem of time. In attempting to reconcile general relativity with quantum mechanics through theories like loop quantum gravity, physicists encounter a stark realization: at the smallest scales of reality, time appears to be irrelevant. The Wheeler-DeWitt equation, which describes quantum gravity, does not even include a variable for time. Instead, it describes a universe that exists as a series of events and relationships, not bound by the traditional flow of past, present, and future. Carlo Rovelli proposes that we abandon the idea of time as a continuous flowing entity and instead see it as a series of discrete interactions. In this view, reality is composed of events rather than things. Imagine watching a movie. The film appears as a continuous motion, but in reality, it's a collection of still images, or frames, shown one after the other. Similarly, Rovelli argues that the universe is a network of interactions and quantum events, with time emerging as a byproduct of how our brains perceive these events. This shift in perspective implies that time is not a background force, but a conceptual tool humans use to interpret change and motion. Without this cognitive framework, there would be no past or future, just a series of interactions happening in the present. Rovelli's ideas challenge the deepest assumptions we have about reality. If time is an illusion, why does it feel so real? Why do we experience the past, present, and future as distinct points along a timeline? Rovelli's answer lies in entropy, a concept from thermodynamics. Entropy is a measure of disorder, and according to the second law of thermodynamics, the entropy of a closed system will always increase over time. The universe began in a highly ordered, low-entropy state, such as the smooth distribution of matter and energy shortly after the Big Bang. Over time, entropy has increased, leading to the emergence of stars, galaxies, and the complex systems we see today. Rovelli argues that our perception of time's flow is rooted in this increasing disorder. Our brains, which evolved to survive in a world governed by cause and effect, interpret the rise in entropy as the forward march of time. From this viewpoint, time's arrow is simply the result of our limited ability to see the world's microscopic details.